Welcome to the DIY Honda Garage channel. The DTC P16E3 represented a communication error involving the battery sensor in the Honda CR-V model 2011 to 2016. The Powertrain Control Module, or PGM-FI, identifies this error when the battery sensor LIN, or Local Interconnect Network Communication, fails. The battery sensor plays a crucial role in monitoring the battery's voltage, providing real-time data to the Engine Control Unit (ECU). Located near or directly on the battery terminal, this sensor helps in battery management, ensuring optimal charging and discharging rates. If this communication is compromised, it can lead to incorrect readings and potentially affect the vehicle's performance. It is essential to address this DTC promptly to avoid further complications in the vehicle's electrical systems. The error DTC P16E3 indicates a failure in the Local Interconnect Network, or LIN communication, regarding the battery sensor. This specific sensor is responsible for relaying important information about the battery's status to the Engine Control Unit, or ECU. The ECU utilizes this data to manage the vehicle's electrical system effectively. Located on the battery's negative terminal, the battery sensor is essential for ensuring the battery is charged correctly and is delivering the right amount of power to the vehicle's electrical components. If the ECU receives incorrect information from the sensor due to a communication error, it could potentially lead to poor performance or even battery failure. This reinforces the importance of maintaining proper communication between the battery sensor and the ECU. Several possible causes can lead to the DTC P16E3 error code. First, loose terminals at the battery sensor can disrupt communication, making it crucial to inspect all connections carefully. Additionally, poor connections within the Local Interconnect Network circuit can create interference, causing communication errors that the ECU detects as faults. Another potential cause is the battery sensor itself being faulty or damaged, which may fail to send accurate voltage data to the ECU. Each of these causes can greatly impact the operations of the vehicle's electrical systems, making it essential to perform a thorough diagnostic check to determine the exact reason for the error. Addressing these causes effectively can help maintain optimal vehicle performance. The symptoms associated with the DTC P16E3 error code can manifest in various ways within the Honda CR-V. Drivers may notice error messages displayed on the dashboard, indicating battery-related problems. In some cases, the vehicle may experience inconsistent behavior, particularly during starting or while idling. Additionally, performance issues may arise, such as reduced battery efficiency or erratic electrical component functionality. These symptoms not only affect day-to-day driving, but could also lead to more significant issues if ignored. Proper diagnostics and repairs are crucial to prevent further complications from arising due to ongoing communication errors within the vehicle's electrical systems. The first step in troubleshooting the DTC P16E3 involves verifying the issue. Begin by turning the ignition switch to the on position, which powers the vehicle's electrical systems without starting the engine. Use the Honda Diagnostic System, or HDS, to clear the DTC and wait approximately 10 seconds. After this waiting period, it is imperative to check for any pending or confirmed DTCs that may indicate ongoing issues. If DTC P16E3 is confirmed, the failure can be replicated, moving to the next troubleshooting step. Alternatively, if no DTCs are indicated, it may suggest an intermittent failure, pointing to potential issues like poor connections or loose terminals elsewhere in the system. In the second troubleshooting step, again check for pending or confirmed DTCs using the HDS. Specifically, you need to verify if DTC P16E3, which refers to LIN communication errors involving the alternator control unit, appears. If P16E3 shows up as confirmed, it signals that the next diagnostic steps need to be taken for this DTC. Otherwise, if DTC P16E3 is not present, focus needs to shift to a deeper examination of other components involved. This check allows you to isolate the problem accurately and dictates the next troubleshooting action, either continuing with P16E3 or addressing any other issues present. Step 3 requires turning the ignition switch to the lock position to ensure safety while working on the vehicle. Next, disconnect the battery sensor 2P connector, which is pivotal for continuing the troubleshooting process. It is essential to check continuity between test points 1 and 2 while keeping the ignition in the lock state and the battery sensor 2P connector disconnected. Test point 1 corresponds to the battery sensor connector number 2, which is typically a blue wire, while test point 2 should be connected to body ground. This will help ascertain if there is a continuous path for the battery sensor signal. If continuity exists, it indicates that the battery sensor wire is intact. If not, it points to further issues requiring repair. In this troubleshooting step, you will need to jump the SCS line using the Honda diagnostic system. This action is crucial in determining if there's a short in the LIN wire. While you're performing this check, be sure to measure the continuity between the battery sensor 2P connector terminal number 2 and body ground. Disconnect the alternator 1P connector and the PCM connector B to see if the continuity goes away when any of these connectors are disconnected. If the continuity does disappear with one of the connectors removed, it suggests that the LIN wire is functioning correctly. If the continuity does not change when disconnected, it indicates the presence of a short that needs to be repaired between the battery sensor, the alternator, and the PCM. Step 5 begins with turning the ignition switch to lock and reconnecting the battery sensor 2P connector, which helps re-establish communication. The next step requires disconnecting the alternator 1P connector to isolate the circuit for further inspection. Check for continuity between test points 1 and 2 at this stage. Test point 1 will connect to the alternator 1P connector number 1, usually marked with a tan wire. And test point 2 connects to body ground. If you confirm continuity between these points, it suggests that the circuitry is intact. However, if continuity is absent, it indicates that deeper diagnostics are necessary, potentially suggesting that the battery sensor itself may need replacement. For step 6, again jump the SCS line using the HDS for continuity verification. After that, disconnect the battery sensor 2P connector and the PCM connector B to facilitate a thorough inspection of the circuit. Measure the continuity between test points 1 and 2 at this point, where test point 1 should connect with PCM connector B number 16, and test point 2 with battery sensor 2P connector number 2. If continuity is present, it indicates that the LIN battery sensor wire is functioning correctly, as it should. However, if there is no continuity, it suggests an open circuit in the LIN wire, indicating that repairs will be needed between the battery sensor and the PCM. In the 7th troubleshooting step, ensure the ignition switch is turned to lock for safety reasons. Next, check fuse number A14, which is a 10-amp fuse located in the under-hood fuse and relay box, to ensure it is functioning properly. This fuse controls crucial components connected to the battery and is essential for proper functionality of the system. If the fuse is intact, you can proceed to the next step, knowing that the circuit is complete. However, if the fuse is found to be blown, It is important to trace back for potential shorts in the +B horn wire between the battery sensor and the under-hood fuse relay box, and replace the blown fuse to restore operation. Step 8 involves disconnecting the battery sensor 2P connector to prepare for a voltage measurement check between specific test points. Under the condition of the ignition switch in the lock position and with the battery sensor disconnected, measure the voltage between test points 1 and 2. Test point 1 corresponds to battery sensor connector number 1, commonly recognized by a white wire, while test point 2 will be connected to body ground. If there is battery voltage present, this indicates that the +B horn wire is functioning properly, allowing you to move forward in the diagnostic process. In the absence of voltage, it indicates an open circuit in the +B horn wire that needs to be addressed before proceeding. The final troubleshooting task entails jumping the SCS line with the HDS to further check continuity. Disconnect PCM connector B while keeping in mind the importance of accurate testing at this juncture. Measure continuity between the test points. Test point 1 being PCM connector B, number 16, and test point 2 being battery sensor 2P, connector number 2. If continuity exists, it indicates that the LIN battery sensor wire is intact. However, if continuity is absent, it confirms an open in the LIN battery sensor wire between the battery sensor and the PCM, indicating that repairs are required in this portion of the circuit. The final repair verification is a critical step to ensure all pre-list tests and potential repairs have been executed successfully. Begin by turning the ignition switch to the lock position to prepare for reconnection. Reconnect all relevant connectors that were detached during the troubleshooting process, ensuring they are secure and free from debris. Next, turn the ignition switch back to the on position to power up the vehicle systems again. Use the HDS to reset the powertrain control module, or PCM, clearing any old diagnostic data. Finally, perform the PCM idle learn procedure and check for any pending or confirmed DTCs to ensure that DTC P16E3 is no longer present and the system is functioning as intended. Preventive maintenance plays a crucial role in ensuring the longevity of the Honda CR-V's electrical systems, particularly concerning the battery sensor and its connections. Regular inspections of the battery sensor and its terminals can help catch issues related to loose or corroded connections before they escalate into significant problems. Additionally, routinely checking the condition and functionality of the battery sensor can mitigate risks of erroneous readings that could affect overall vehicle performance. Another essential aspect of maintenance is ensuring that the powertrain control module, or PCM, is updated with the latest software. This updated software can improve communication and system performance, reducing future instances of DTC P16E3 occurring. In conclusion, the DTC P16E3 highlights critical issues related to the communication between the battery sensor and the powertrain control module. Addressing potential causes, such as loose terminals, poor connections, or faulty components, is vital in restoring the vehicle's optimal performance. The troubleshooting steps outlined should be followed carefully to ensure accurate diagnostics and repairs. Moreover, preventive maintenance is recommended to preempt similar issues in the future, emphasizing the significance of regular system checks and updates. By taking these steps, vehicle owners can maintain their Honda CR-V's efficiency and reliability over time. Please like and subscribe to the channel. See you next time.